OCR A-A-Level Chemistry 2017 Paper 2 Walkthrough. Let's get going. So our first question, a chemist compares the rate of hydrolysis for 1 chloropropane and 1 bromopropane in ethanol. Which reagent in aqueous solution should be used? Well, if we're testing for our two halogens, our haloalkanes, then we're going to be looking at silver nitrate, which is B. How can the molecule below be described? Well, here we've got a ring, but it's not a benzene ring, so it's going to be alicyclic, and it's not going to be aromatic, so get rid of A. This one doesn't have alicyclic in it, and neither does this one, so it's D, but just check. Saturated, well, it's not got any double bonds in it, it's in the way. It's not got any double bonds in it, so it's going to be D, because it is both alicyclic and saturated. Question 3. Complete combustion of an organic compound forms 40 centimeters cubed of carbon dioxide and 40 centimeters cubed of water vapor under the same conditions of temperature and pressure. Which molecular formula could the organic compound have? Well, it's not going to be D, because D contains a nitrogen. So that's off the list, first of all. So now we do our MRNVC. So if we have 0.04 decimeters cubed of CO2 and H2O, 0.04 here. Now if they're under the same conditions of temperature, let's just use what we know. Let's use the 24 decimeters cubed rule. 1 mole is equal to 24 decimeters cubed. So then we're going to do, excuse me while I get my calculator, 0.04 over 24 gives you 0.016, and that's going to be the same answer for this. So these are in a 1-to-1 ratio. Let me just... some molecule plus O2. Okay. So these are in a 1-to-1 ratio. So the carbons can only come from here. The carbons in the CO2 can only come from X, and the hydrogens can only come from X. So if we look at the ratio of carbons to hydrogens, we've got 0.016 to 0.016 times 2, so it's a 1-to-2 ratio. So we're looking for a organic compound with a ratio of CH2. So first one, 3-to-8, that's not right, so just cross that one out. B, not that one, cross that one out. C, 2-to-4, that's 1-to-2, that's awesome, so it's going to be C, and it can't be D like we said earlier, because it's got a nitrogen in it. So, number 4, which molecule is a Z isomer? Well, the way to remember which one's E and which one's Z is that Z isomers have the high priority groups on the same side. And what are we looking for? Well, we're using our Kahn-Ingold prelog principles, which state that the higher the atomic mass, the atomic number, the higher the priority. So, looking at molecule A, which is higher out of carbon and hydrogen, well, it's going to be this one. Which is going to be more fluorine or hydrogen? Well, it's going to be fluorine. These are on opposite sides, so it's E. Chlorine versus hydrogen, well, it's going to be chlorine and fluorine versus carbon. Well, it's going to be fluorine. Fluorine versus chlorine, it's going to be chlorine. Hydrogen versus carbon, it's going to be this one. and these two are on the same side of this molecule, so this doesn't even count as a stereoisomer. So this one's on the same, these two are on opposite sides, these two are on opposite sides, so B is our answer. What type of reaction has the greatest atom economy? So how do we define atom economy? It's our MR of our desired products over our total MR. So looking at our options, well, addition stands out because addition, all we're saying is some molecule A plus some molecule B gives us AB and nothing else. So what's this atom economy going to be? Well, it's going to be 100% because our molecule of our desired product is equal to our molecular mass of our total products. So it's D. That's an awful D. There you go. 4 atoms, 1 to 4, are labelled in the structure below. Which atom has a trigonal planar arrangement of bonds around it? Well, what do we know about trigonal planar? It's got 3 bonded regions. So, look at this. Well, this methyl group here is going to have 4 bonded regions, so it's not 1. This one here has got, would you look at that, 4 bonded regions, so it's not going to be 2. Carbon 4 has got 3 things bonded to it, but don't forget nitrogen has a lone pair, which acts as its own bonded region, so it's not going to be 4, so it leaves us 3, and let's just check. 1 bonded region, 2 bonded regions, 3 bonded regions, and no lone pairs, so it is atom 4. Which molecule is a secondary amine? And note the amine and not amide. So, secondary amine means NH R. So looking for that. Well, in A, yep, that's got 2 R groups and 1 H, so A is looking like a likely contender. In B, well, this nitrogen's bonded to 2 as well, but the one next to the nitrogen is bonded to a carbonyl group, so it's not going to be B, because this is an amide. Same can be said for C, and also it's a tertiary amide anyway. And this is a tertiary amine because it's bonded to 3 groups, so it's going to be A. What is the number of chiral centres in the molecule below? So if we start from the left-hand side and work our way right, so we start with a benzene ring. Well, there's not going to be any in a benzene ring. I probably should have defined chirality at the start. Chirality has 4 different groups, X, Y, Z, and we'll go with W, because why not? So all of these are double bonded, so they can't have 4 different 4 different groups attached to them. So we start with this one here. Well, one's bonded to a nitrogen, bonded to a carbonyl group here, bonded to a benzene ring here, and bonded to a hidden hydrogen. So yeah, this is 1. This one's double bonded to an oxygen, so you can't count this one. Nitrogen can't count because it has to be a carbon atom. This one here is bonded to a carbonyl this way, an amine this way, and I'm not sure what you'd call that, but a carbon with a sulfur on, so this is going to be number 2. This one here is bonded to that way, bonded to a nitrogen that way, and bonded to a sulfur that way, so add another hidden hydrogen, so that's going to be 3. And then nitrogen you can't do, sulfur you can't do. This one here is bonded to a nitrogen, this group here, and a hydrogen, and the carboxylic acid group here, so this is going to be 4. This one's all bonded to an oxygen, so it can't count, and all of these are H3 surrounded, so the answer is C. What is the molecular formula of the compound below? Well, there's two ways to do this. I'm going to show you the slow way first, and then I'm going to show you the way I do it that works really well with big molecules and things like that. So, obvious method: 1, 2, 3, 4, 5, 6, 7, 7 carbon, and then 2 here, 2 here, 3 here, 3 here, and 2 here. And notice all of these make 4 bonds on the carbon. So I've got a hydrogen there and 1 there. So 3, 6, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, CH14. But as you can see there, that got quite messy and also quite complicated. So the way I do something like this, again, especially if it was a big molecule, I've had molecules like testosterone come up in the past that are just an absolute nightmare to go. You've got 2 there, 4 there. It's horrible, and I don't like it, and I'm not going to do it. So the way I would do it is you go 1, 3, 4, 5, 6, 7. So you got carbon 7, and then you go. Well, I've got a benzene ring. I've got a ring here, so that's -2 hydrogen. If I've got anything else, that would mean I'd have to -2 hydrogen. Well, I've not got a double bond, and I've not got any other. I've only got single bonds. It's a saturated compound. So I've got 1 ring, so -2 hydrogen. So go C2N plus 2 minus 2. So this and this cancel out, so it's C7H14. And this is something called DBE, and the equation to use DBE is CnH2n plus 2 minus 2 DBE. And what DBE means is double bond equivalent. So a ring or a double bond has a DBE value of 1, and a triple bond has a DBE value of 2. So if we had that was drawn absolutely horribly. If we have a benzene ring here, if we draw the calculate structure, so we've got 1 ring, so that's 1 DBE, then we've got double bonds, so that's 2, triple bond, another double bond, so that's 3, another double bond, so that's 4, so that's 4 DBE. So we have C6H2 times 6 plus 2 minus 4 times 2. So we have C6H12 plus 2 minus 4 times 2 is 8. So we have C6H14 minus 8, which is C6H6. And it's just stuff like that. That was just some more difficult example for what I find to be the simpler method. Equal amounts of the 4 compounds are added to the same volume of water. Same volume of water. Which compound will produce the most acidic? So here we've got an amide, CH3C. We've got that. Now if you add water to that, it's not going to do much, so A is gone. CH3COOH, well, that's carboxylic acid, and when you dissolve that in water, it's still going to be an acid. So B is a strong contender. CH3COOCH3. That's an ester, that's not going to do anything in water. Which leaves us with D, which is a acyl chloride, and if we add water to that, well, what's going to happen? We're going to turn it into CH3COOH, and then we've got a hydrogen going spare. So we've reacted it with water. So we've got a hydrogen going spare, and we've got a chlorine going spare. What are we going to make? Well, we're going to make HCl dissolve in water, and you're going to get hydrochloric acid. So we've got a strong acid and a weak acid versus in B just a weak acid. So the answer is going to be D. Question 11. The compound below is analysed by proton NMR. How many peaks are observed? So first off, it is symmetrical. That's going to help. So we've got one peak. I've just drawn directly down where I want to go. So we've got two hydrogens here. So we've got one environment. We've got another two here and another two here. So we've got two here and here. That's going to share a peak, so we'll call that 2 and 2. This has no hydrogens in it at all because all 4 bonds are there. And then we've got one here and one here that are symmetrical, so that's 3. And 3 is answer C. 0.1 moles of this molecule here are reacted with 0.1 moles of aqueous sodium hydroxide. How many molecules of water are formed? So first of all, we're making molecules, not moles. That explains why all our powers are very high. So we're going to do our M, R, N, and hopefully what you see here is this is a dibasic acid. It's got 2 hydrogens. When it dissociates, it's going to dissociate into 2 hydrogens. If I just draw this at the top, we've got COOH, COOH, and that's going to dissociate into that OO minus plus 2H plus. So, bearing in mind we're forming water because we're neutralizing. I've done that right in the way. We're forming water. We're going to need 2 moles of sodium hydroxide for every 1 molecule of this compound here. So if we just call this, I'm just going to put Ca for carboxylic acid, plus 2 NaOH gives us water and some disol. So 0.1 moles of our carboxylic acid is reacted with 0.1 moles of this. Now, one of these has to be our limiting reagent, and it's going to be the sodium hydroxide, because we've got this in excess. This, in realism, will only react in a quantity of 0.5 moles because it's in a ratio of 1 to 2. So it's going to have half the number of moles react. So it's 0.5 moles, 0.05 that should be, 0.05 moles of this. So to create our water, like we said, that will create 2 moles of water, so that will be 0.1. Let's create 2 moles of water because we take 2 OHs and 2 hydrogens from our carboxylic acid. So 0.1 moles of that, so 0.1 times Avogadro's constant, 6.02 times 10 to the 23. Well, that's just 1 times 10 to the minus 1. So take that power off, take that power off, and you get 6.02 times 10 to the 22, which is 6.02 times 10 to the 22A. Which reagents can be used to prepare this molecule here? Well, if we draw this molecule out, we get that. And this is an amide with a D rather than an N, because the carbon is double bonded to an oxygen and then bonded to the amine group. So if we split this down the center, how are we going to create it? Well, we're going to react an amine with what's going to give us this group here. Well, it's going to be a acyl chloride. So, A. Well, this is an acyl chloride, and it's the same carbon chain length, and then an amine. So A is good. Let's just check the others before we do anything brash. Well, this is an amide already, so this isn't going to react. This is a carboxylate salt, so this isn't going to react. And this is a ketone, so this isn't going to react, so it's going to be A. Ethane reacts with chlorine by radical substitution to form chloroethane, which radicals is or are present in the mechanism. So let's just draw out our mechanism really quickly. So we've got initiation, that's when our no radicals, so chlorine, go to two radicals. And then we've got propagation, wasting a lot of time writing this out, propagation, and that's when we have our one radical into a different radical. So we take our C2H6, which is our ethane, plus our chlorine radical, that's this side, to create, what are we creating? C2H5 plus HCl. So that's our radical on that side, and you take your C2H5 radical and you react it with Cl2 again. That gives you C2H5Cl plus Cl radical. So you can do termination, but termination just involves all of the radicals that we've done so far. So what radicals have we got? Well, we've got chlorine here, so that's 2, and we've got C2H5, which is 3. What haven't we got? Well, we haven't got a hydrogen. So it is 2 and 3, which is C. So which compounds is or are structural isomers of C6H12O2? So let's go through them one by one. Hexanoic acid, 1, 2, 3, 4, 5, 6. Double bond to an oxygen. So what have we got here? Well, we've got C6H, work through this manually or with the DBE method I did earlier. I'm just going to rush this for you, is H12, and that's O2, because that's 3, that's 5, that's 7, that's 9, that's 11, and then there's none here, but there's one here, so that's 12. Next is ethyl. Hang on, I'll take that off before I forget. So 1 is awesome, so cross out C. Ethyl butanoate is 1, 2, oxygen, 1, 2, 3, 4. So we've got 1, 2, 3, 4, 5, 6. C6H again. You can use the DBE method or you can count them out. So it's 12O2. Again, just check 3. That's 5. That's none there. That's 7. That's 9. And that's 12. And then finally, you've got propyl propanoate. Hang on. 2 is fine, so D can be crossed out. And you've got propyl propanoate. So there you go. And then you have got 6 carbons, so C6. H, again, it's 12, but you can just check is it's 3, there it is, 5, 7, skip this, 9, 12, so, and then O2. So it is all 3 of them, so it is A. This question is about unsaturated hydrocarbons. Compound A and compound B are isomers. Compound A has a lower melting point than compound B, suggest why. Well, the first thing, we have melting point mentioned, so we're going to mention London forces. So, compound A has weaker intermolecular forces brackets London forces which require less energy to overcome. And why is that? Well, we can look at our question. What's the only difference between compound A and compound B? Well, it's this methyl group here. So, as compound A has a methyl group, so has a lower surface area. Compound Z exists as cis and trans stereoisomers. Name compound C. Well, we've got 1, 2, 3, 4, 5, 6. So we've got 6 carbons, so it's going to be hex. We've got a double bond here, so it's going to be something N, and we've got an alcohol at the end here, so it's going to be ol. Now, we need to put our numbers in. So this is here. It's attached to the first carbon, so we're going to say 1 ol, and then we're going to, this is first, this is second, this is third, so it's 3 hex, 3, and 1 ol. Now we could go 1, 2, 3, 4, 5, 6, 6, sorry, yeah. You could do hex 3 in 6 ol, but the key thing with naming molecules is you try to keep the numbers at the front, so like this 3 and this 1 here, as low as possible, and always stuff like alcohol groups and stuff at the end will take priority as number 1 for that to be the case. Define the term stereoisomers. So this one's nice, easy, couple of marks, well, 1 mark, and all we're going to say is same structural formula but different arrangement of atoms in space. Different arrangement Awesome, 1 mark instantly. Next question. Draw the structures of the cis and trans stereoisomers of compound C. So, for those of you who can't remember, compound C was this here, CH2, CHOH. Right, so cis means they're on the same side, and trans means the high priority groups are on opposite sides, and that's the same as E and, get it the right way around, that's the same as Z and E, except that to be cis and trans, it's got to have the same hydrogens in it on both sides. So for cis, we're going to do our carbon-to-carbon double bond, and then we've got our hydrogens on the same side, and then we're going to do the rest of our group, so CH2, CH2OH, and then on this side, CH2, CH3. And we're going to do the same with this one. So C, double bond C, and then the H's have to be on opposite sides. That's CH2, CH2OH, and then CH2, CH3. Next question. The C to C double bond group in an alkene contains a pi bond. Complete the diagram below to show how p orbitals are involved in the formation of a pi bond. So these here are little wedges, are our sigma bond, and those are really strong. Now for a double bond, what we want is a C to C sigma bond, and then we take our vertical p orbitals, and then they become overlapped to form the double bond. If you can define a double bond, you'll remember that it is the sideways overlap of p orbitals. So nice and quickly, we just go p, 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 p. We've drawn our orbitals, and then they're going to become. So just make sure we label them. P orbitals, pi bond. Compound D, shown below, reacts with hydrogen bromide by electrophilic addition. A mixture of two organic compounds, E and F, is formed. Suggest how a hydrogen bromide molecule can act as an electrophile. Well, what does electrophile mean? It just means electron pair, acceptor, electron pair. So, out of hydrogen and bromide, or bromine, which is more likely to attract an electron? Well, it's going to heterolytically split, and bromine is going to become more electronegative, whereas hydrogen is going to be more electropositive. So, which is going to attract an electron pair more? Well, it's going to be the more positive one. So, hydrogen atom will attract an electron pair. Draw the structures of the two organic compounds E and F. Well, we're just doing addition. So, if we were to take our double bond and split it, one's going to take the hydrogen and one carbon's going to take the bromine. Then we draw the rest of our molecule. And then on the other product, we're going to swap the order around. So C to C, and then we're going to put our bromine on the other side and our hydrogen on the other side, and draw the rest. CH2, CH3, CH3, CH3. Just check I've got that. Yeah, awesome. Outline the mechanism of the reaction between compound D and hydrogen bromide to form either E or compound F. Well, we've got C, double bond C, CH3, CH3. What was this? It was one hydrogen and CH2, CH3. Yep, that's right. Okay. So, if we take our hydrogen bromide, what we're going to do, well, this is going to become a dipole, this is going to become a dipole, shift our arrow this way, and then our arrow is going to go from our double bond. We're donating the electrons towards the hydrogen. Remember, that's what a curly arrow means, a movement of a pair of electrons. So, what does that give us? Well, it gives us C, H, CH3, CH3, and then C, CH2, CH3, excuse me, and H there, and then this becomes positive, and your bromine is negative, and then it just moves to there, remember, because you're moving your electrons into the bond, so that becomes CH3, CH3, HC, Br, H, CH2, CH3. So, which of E or F is the major product? Well, the major product is always going to be the most stable. How do we know which one's the most stable? Well, it's going to be the carbocation with the most order. And what I mean by that is secondary is more stable than primary, tertiary is more stable than secondary, and quaternary is more stable than all three. So what that means is the number of carbons attached to it determines how stable it is. So if we go back and find our molecule, which is that CH3, CH3, C, C, that's an H, that's an H2CH3. So, if we pretend we're going through our mechanism, if we put our bromine here, if we put our hydrogen here, then our carbocation is going to go here, so our bromine is going to go here, and well, that's one carbon, so that's its surrounding one, so that's 1, and that's 2, so that's on position 2, and it's got 2 surrounding. Now, what if we were to swap them around? So, if we were to hydrogenate this one, so that's H, and instead this one, this becomes our carbocation. Cation obviously means positive ion, so we've got 1 carbon here, 2 carbon here, 3 carbon here, so that makes this tertiary. And tertiary is obviously more stable than secondary, which is what we had last time. So the bromine's going to go here, and then what do we call this? Well, we'll put a bromine here. As always, go along the longest carbon chain, so it's going to be 1, 2, 3, 4, 5. So pentane, it's going to be some form of pentane. And then we've got a methyl group on the 2, and we've also got a bromo. So 2 bromo, run out of space, 2 methyl pentane. Is that right? Yes, it is. Awesome. So, explanation, Markov-Nikov principles. State that the secondary carbocation, the tertiary carbocation is more stable. Myrcene is a naturally occurring hydrocarbon containing more than one carbon-to-carbon double bond. Reaction of 204 milligrams, so straight up write that as 204 times 10 to the minus 3, reacts with hydrogen gas and produces a saturated alkane, and that means that there's no C to C double bonds. Calculate the volume in centimeters cubed, that will be important, and then in room temperature pressure. Well, what does room temperature pressure tell us? It's 24 decimeters cubed is equal to 1 mole of gas. So let's be sure to show our working. So we're going to do our little grid, so M, MR, N, V, C. So we've got our myrcene here. Our mass of this is 204 times 10 to the minus 3. Our MR, well, 12 times 10 is 120, plus 16 is 136. So 204 times 10 to the minus 3 over 130 gives us 0.15, no, sorry, 1.5 times 10 to the minus 3. So then we need to add some number of hydrogen gas molecules to create a saturated alkane. Well, everyone knows that a saturated alkane has the formula CnH2n plus 2, so in this case we're looking for C10H22. So what do we get when we subtract 16 from minus 22? Well, we get H6. So divide that by 2 because hydrogen's diatomic, and you get a 1 to 3 ratio. So that's 4.5 times 10 to the minus 3 because you times it by 3. Then you times that by 24. That gives you your volume in decimeters cubed. So 4.5 times 10 to the minus 3 times 24 gives you 0.108. So you then times that by 1,000 to get centimeters cubed is 108 centimeters cubed. Beta-carotene is a naturally occurring unsaturated hydrocarbon found in carrots. A beta-carotene molecule contains 40 carbon atoms, has 2 rings and a branched chain. 0.02 moles of beta-carotene reacts with 5.28 decimeters cubed of hydrogen gas to form a saturated hydrocarbon. Using molecular formulae, construct a balanced equation for this reaction. Okay, so we're going to do our little grid again, M, MR, N. Don't put V and C in just for the sake of it. So we've got 0.02 moles of beta-carotene. So if we have 5.28 decimeters cubed of hydrogen, what's that in moles? Well, 5.28 divided by 24 gives us 0.22. So what does that tell us? Well, it's going to react with 11 molecules of hydrogen, because that's in a 1 to 11 ratio. So there must be 11 double bonds in beta-carotene. So we're going to use our little or DBE from earlier. So we know that it's C40, and then H is going to be 2N plus 2 minus 2 DBE. So it's got 11 double bonds, so that's 11 DBE, plus 2 rings, so that's 2 DBE, and then the branch chain isn't important, so that's 22, that's 13, so 2 times 13, so C40, H, so 2 times 40, plus 2, minus 2 times 13, gives us 56, so it's C40H56, plus we know it's 11H2, and that's going to give us a fully saturated molecule. So what are we looking for here? We're adding 22 to this, so it's just going to be C40H56 plus 22 is 78, and there shouldn't be any other products. This question is about the chemistry of aromatic compounds. Benzoic acid can be nitrated by concentrated nitric acid in the presence of concentrated sulfuric acid as a catalyst. as shown in equation 17.1. The organic product of this is 3-nitrobenzoic acid. Outline the mechanism for the nitration of benzoic acid, and this really crucial part, show how H2SO4 or sulfuric acid behaves as a catalyst. So in which case we've got to do our first step, which is we take our H2SO4, there it is, H2SO4, and we react it with our nitric acid, and we need to generate NO2 because we're nitrating a benzene ring. So NO2 plus we're going to have water, and then we're going to have HSO4 minus, and the reason we know it's HSO4 minus is because this has no charge on this side of the equation, so it can't have charge on this side of the equation either. So now we have our NO2, so we take our benzene ring, and we take our NO2 plus, and then because this is a positive ion, I'm going to put the plus on the other side, because this is a positive ion, the electron pair are going to donate to it, so then we're going to get, gosh, that's an awful hexagon, then you're going to get this attached to the benzene ring, and then you're also going to have a hydrogen, and then the hydrogen's going to donate its electrons back in, and you've got to do this little horseshoe shape that can't extend past, make sure you put your plus sign in by the way, it can't extend past this point. That's just the rule that the examiners have come up with. So you have that, the hydrogen redonates its electrons in, and then you get, after that, you get, hopefully you'll be able to fit this all in one line. It has just auto-drawn a pentagon. That's not what I wanted. There you go. It will initiate your benzene ring. You put your nitrate group on there, and then you generate an H plus ion. And then what your H plus ion does is it reacts with your HSO4 minus from earlier, and it generates H2SO4. So we can say it's a catalyst because it's regenerated. H2SO4 is a catalyst as it is regenerated. I've just realised I forgot the other group on the benzene ring, so make sure you do that. I'll just do it quickly now. If this is going to be on position 3, then it's going to be 1, 2, 3, it's going to be here, so COOH. Again, hopefully you'll have realised this long before I did. COOH, and here COOH. Sorry about that, folks, but there you go. The mechanism is still very much the same. A chemist carries out the reaction in 17.1 using 4.97 grams of benzoic acid. Student obtains 3-nitrobenzoic acid as an impure solid. The student purifies the solid to obtain 4.85 grams of 3-nitrobenzoic acid. Describe a method to obtain a pure sample of 3-nitrobenzoic acid from the impure solid, determine the percentage yield, and check its purity. So, like always with 6 markers, we're going to split it up into little bits. So, describe a method, we'll call part 1, determine the percentage yield, part 2, check the purity, part 3. So, we are separating impure solids. How do we do that? Well, we're going to recrystallize. So what are the steps involved in that recrystallize? There it is. So we're going to dissolve our products, impure product, just be absolutely clear, impure product in the minimal amount of hot solvent. And what does that do? Well, it removes all of the impurities. It dissolves all of the impurities. Dissolves all impurities. And then you're going to cool it. So cool the solution, and your pure sample recrystallizes. Hence the name. Very cool. Pure sample recrystallizes, but your impure sample doesn't. I'm not going to put that because it's not really relevant, but it's good just to know. And then what do you do with it? Well, you're going to filter it again. And that will give you your pure solid. And then all you've got to do is wash and dry sample. With cold solvent. I'm going to do part 3 while I'm in a righty mood before I get to the maths. So part 3, check its purity. So, part 3. So, what are the things we can do? We can obtain its melting point. And compare to known values. And then just for any extra marks we can get our hands on, if it's impure, melting point will be broad and slightly lower than expected. You can also do other methods. TLC would work. What's it called? Spectroscopy also would work. I've not left myself a lot of space for this maths. Let me just 4.97 and 4.85. So we're going to do our little grid again. MMRN. This is part 2. So this is our benzoic acid. And this is our nitrobenzoic acid. So I've said it and I've forgotten how much of each do we get. So we obtain 4.85 grams. And we put in 4.97. So we know this is going to be in a 1-to-1 ratio. We don't need to worry about anything else because we did the mechanism earlier. So what's the MR of benzoic acid? Let's just draw it out again. COOH. So what have we got? We've got C7H1, 2, 3, 4, 5, 6. C7H6 and then 2 oxygens. So what does that give you? 7 times 12 is 84. Plus 6 gives you 90, and then plus 32 gives you 122. So do 4.97 over 122, gives you a number of moles, which is 0.041. I'm just going to leave it as answer. So answer times, okay, we added in a nitrogen, and what that means is we have, gosh, that's actually a horrible hexagon, NO2, and what that means is we've taken off a hydrogen, so we've got C7H5, O2, and then O2, N, O2, so O4, but we'll do that as we go. So 7 times 12 is 84, plus 5 is 89, plus 32 gives us 121, add 14 for the nitrogen, gives us 135, add 32 for the oxygen, gives us 167. So now we're doing 4.85 was our actual obtained, and then we want to do answer times 167. So 0.041 times 167 gives us 6. So we were expected to make 6.8 grams, and we only made 4.85. So if we did 4 over 6.847, that gives us 4.85 over 6.847 gives us 71%, or 0.71, and then to find it as a percent, you times it by 100, so you get 71%. A student investigates the relative ease of nitration of phenol, benzene, and benzoic acid. Student finds the condition required for the nitration of each compound are different. State the trend in relative ease of phenol, benzene, and benzoic acid. Well, two things tell me this is going to be a really short answer. It's 1 mark, and it's state rather than explain. That's the next one. So, literally, all we have to do is phenol is the most reactive. Or easy to nitrate, I don't mind how you phrase it. Benzoic acid is the most difficult, or least reactive. As promised, apply your knowledge of the bonding in arenes to explain the trend in part BI. So if we go back to our molecules here, what happens is in phenol, the lone pairs in the oxygen kind of donate their negativity, electronegativity, we know that, to the phenol. And what that does is it makes it more electron dense. It doesn't make it negative, it just means it has more negative charge in that benzene ring. And what that means is it will react more with electrophiles like nitrogen. Nitro group. Benzene is your default, you don't need to mention that. And then benzoic acid, well, if we have oxygen here and OH here, I've just said these are electron withdrawing. Well, they're not going to withdraw from the benzene ring, they're going to withdraw from this carbon. Which means that the carbon's going to kind of take some from the benzene ring. Which means the benzene ring is going to become less electron dense. So, less electron dense, and so react with electrophiles like the nitrate group less or slower or require more conditions. So, the phenol OH group is electron donating. This delocalizes the benzene ring. This delocalizes the benzene ring. Creating an area of high electron density. Which reacts more readily with nucleophiles. Nope. More readily with electrophiles. Got to get it right at some point. Okay, so, and then you gotta flip that on your head, on its head even. The benzoic acid COOH group is electron withdrawing. This creates an area of low electron density, making it more difficult to react with nucleophiles. Electrophiles. I keep doing that. An area of low electron density. Making it more difficult to react with electrophiles. Making it more difficult to react with electrophiles. I'll tell you what it is. It's just the fact I keep saying electrons. Just gets in my head. There you go. Also, just a bit of a tip here. I know I just got it wrong about 3 times, but a little bit of help for you is if you struggle to remember, you know, if it's a electrophile or a nucleophile, well, its nitrate group is NO2+. Now, we've got a positive charge here. Is a positive charge more likely to accept electrons or donate them? It's more likely to accept them because it wants to turn this positive into no charge at all. And likewise, if you have a negative ion like OH, is it an electrophile? Is it a nucleophile? Well, it's going to want to get rid of its electrons so it can become neutral. So it's going to be a nucleophile. A student synthesizes 3-bromophenylamine shown below, starting from nitrobenzene. Complete the flowchart showing the structure of the intermediate and the formulae of the reagents for each stage. So if we draw our nitrate group, oxygen there, put its lone pairs on, oxygen here, put its lone pairs on, and then we're going to have a little kind of temporary bond there. So what's happening here? Well, the lone pairs are going to pull away from the nitrogen, so the nitrogen's going to have to pull away from the benzene ring. Pull like the electron density, not physically. So the electron density of the benzene ring is going to decrease. So what does that mean? Well, it means it reacts with electrophiles less, like we said last time. So we're going to need our bromine, obviously, to brominate, but we're also going to need bromine or a halogen carrier. So that should be Br3. What does that give us? Well, it does tell us in the question, it puts it on position 3. But if you didn't know, that is in your spec as one of the directing groups that you should know. I know that's not helpful, but it is on there. And then we need to reduce it. Well, how are we going to do that? We need to add hydrogens to it. So hydrogen plus, that's a big part of it, or some sort of acid, just put HCl, yeah, and then we're going to need some sort of catalyst. In this one it is tin. Again, that's just something you got to know. Another student attempts the same synthesis but carries out reduction, that's that step there, before bromination. What's he doing? The student was surprised to find that the 2 structural isomers of 3-bromophenylamine had been formed instead of the desired organic product. Explain this result and suggest the structures of the 2 isomers found. So if he's gone from NO2 to NH2, well, problem is NO2 is 3 directing, NH2 is 2 4 directing. Again, that's one of the ones you should know, but don't worry, if you don't, you can easily work it out with the method I showed you. So NH2 is 2 4 directing, that should be a comma, not a dash, is 2, 4, 2, 4 directing. So bromine plus ion will have substituted to positions 2 or 4. And that 2 or 4 is how we get our, 2 structural isomers. So if it's amine at the top, first one's going to be at position 2, so that's Br there, and then the second one's going to be there, NH2, and it's going to be position 4, which is here. This question is about organic compounds containing nitrogen. Sodium cyanide can be reacted with many organic compounds to increase the length of a carbon chain. 1-chloropropane reacts with ethanolic sodium cyanide by nucleophilic substitution. Ethanolic just means dissolved in ethanol. And nucleophilic substitution, they've even told you the name of the mechanism. Outline the mechanism for this reaction, include curly arrows, relevant dipoles, and the structure of the organic product. So we take our reactant, which is 1-chloropropane, so H there, CH2, CH3, and then because one of these has to be electropositive and one of these has to be electronegative, it's going to be the one the electrons sit closer to, which in this case is chlorine, and you know that because chlorine is closer to fluorine than carbon is in the periodic table. So because they sit closer to the chlorine, we're going to draw our curly arrow in there. And then nucleophilic substitution. So we're substituting a nucleophile. And like I said a few questions ago, a couple of minutes ago, a nucleophile, well, it loves nucleuses, it loves positive charge. So what's it going to do? It's going to give off electrons, so give away electrons. What's more likely to give off an electron? Well, it's going to be a negative ion, which in this case is cyanide. So put a negative charge next to that, and it's going to donate its electrons to that carbon because the carbon's electropositive, and it's going to give us our extended sorry, I can't speak them right at the same time. It's going to give us our extended carbon chain, and because we need to conserve charge, and also we can't have 5 molecules bonded to the carbon, it's also going to eject the chlorine to become a chloride ion. Compound G is used to synthesize compounds H and I as shown in the flowchart below. Complete the flowchart showing the structure of compound G and the formula of the reagents for reaction 2 and 3. So if we look at compound I, just scroll so I can see a little better. If we look at the differences between our center molecule and compound I, what's the difference? Well, it's this carboxylic acid group here. That's a horrible circle. So we need to go from a nitrile group to our carboxylic acid. How are we going to do that? Well, what's the difference between them? This has got OOH difference to this. So what's that going to be? Well, it's going to be water. And then we need to get rid of this nitrogen somehow. How are we going to get rid of this nitrogen? Well, we're going to turn it into ammonia. So how do we turn nitrogen into ammonia? We need to donate protons, so we're going to use hydrochloric acid. Call that AQ. So next molecule, reaction 1. So this time we're going into the hydroxynitrile group, and we're adding sodium cyanide. So we're adding this group here, and we're also adding a H plus ions. So how are we going to do this? So obviously we need to take away our cyanide group, so it's going to be C, H, H, and then we're adding our hydrogens, we're going to add this hydrogen here, so it's going to be an aldehyde. So in this case, it's methanol. And then reaction 2, how do we get from a nitrile group to an amine? Well, what's the difference? It's hydrogen. Yeah, it's hydrogen. Specifically, you can put a 2 here, but you don't have to. And then you need a catalyst, and like always with reduction or hydrogenation, it's going to be nickel. Compound H reacts with dilute hydrochloric acid to form a salt. Explain why compound H can do this and suggest a structure for the salt formed. Okay, so if we go back to our molecules from the last question, compound H is this amine here. So we're reacting it with an acid to get a salt, so what's compound H going to be? Well, it's going to be a base or an alkali, because base plus acid gives you salt and water. So how can we make this a base? Well, a base always accepts a proton, so we've got protons from the acid. Where's it going to go in this molecule? Well, it's going to go on the lone pair of the hydrogen to form a positive ion. So it's going to look like this. N, H, 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 and then it's going to be positive. So if we know that that's what that this is acting as our base and it's accepting a proton to form a salt, what's the salt going to look like? Well, it's going to look like our acid here. So C, 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 N, H, 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 a lot of H's, H, 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 OH, I think it is. So it's going to be plus, and then what else do we have going? Well, we've got hydrochloric acid. So normal salt is like sodium chloride. So this chloride like that is awesome. And then obviously we need to do the first part. We need to explain it. So what are we going to say? We're going to say the amine group acts as a base, acts as a base to accept H plus ions to form a salt. Compound I is the monomer for the biodegradable polymer J. Draw 2 repeat units of polymer J and suggest why it's biodegradable. Well, if we go to compound I contains an alcohol and a carboxylic acid. So what's it going to do? Well, it's going to form polyester. So if I just redraw this so we know what we're looking at more easily, all I've done, by the way, is move this OH here and move this hydrogen here, and you're allowed to do that. That's called free rotation, and it can happen as long as you don't have a double bond. So if we do that, then we're drawing 2 repeat units of it. So we've got C to C with an OH here, an H there, an H there, an H there. No, not an H there. Let me get rid of that. Double O here, and an OH here. So if we draw that again, what are we going to do to this molecule to form a polyester? Well, an ester contains the group there you go. Ester contains the group C double bond O O C, like that. So how are we going to create that? Well, we're going to get rid of this here. I'm just going to draw this in a straight line. So we've got our double bond O here, and then the O from the OH molecule is going to become our ester link here. And then this is going to happen again here. If you see double bond O, O, like that. Now, it only wants 2 repeat units, so we're going to draw that. And because we end with an O, we cut this O off there. So rub it out. So it looks like that. So, why is it biodegradable? Well, things are only biodegradable if you can break down this link here with hydrolysis. So that's all we've got to write, is the ester group can be broken down by hydrolysis. The repeat unit of nylon 6,6 is shown below. Draw the structures of 2 monomers that can be used to form nylon 6,6. So we know we've got a polyamide here because the nitrogen and the oxygen are next to each other. So how can we form a polyamide? Well, it can either be a dicarboxylic acid and a diamine, or it can be one that contains both groups. But from what we've got here, the fact that our repeat unit is so long, we know that it's not going to be a dicarboxylic acid diamine. So what are we looking for? Well, just here we've got double bond O, some backbone double bond O, and just here we've got NH, some backbone NH. So what does that tell us? Well, our 2 at the moment broken into parts looks like this. Oxygen 1, 2, 3, 4, 5, 6. And then our other molecule looks like this. NH 1, 2, 3, 4, 5, 6. NH there. I might move that along in a bit. So, what did I say? I said dicarboxylic acid and diamine. Well, this has the potential to form a dicarboxylic acid. All we have to do is chuck OHs in there. So that's that one done. And this has the potential to be an diamine if we just chuck an extra hydrogen in there. And also, just a quick checking method. We take the group we've added, we take the other group we've added, and it's water. So it's a condensation polymerization, so that we know we are on the right lines. A sample of nylon 6,6 has a relative molecular mass of 21,500. Estimate the number of repeat units in this sample, give your answer as a whole number. So we want to find the molecular mass of our repeat unit. It's going to be big. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I didn't mean to put that notion in there, so there's 12. Just check that because I've probably just confused some people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it's C12. And then we have 2 double bonds. So we're going to get rid of H2N plus 2 minus 4 because we've got 2 double bonds. So that gives us 2N minus 2. Minus 2, chuck in our other molecules, O2, N2. So C12H, 12 times 2 is 24, minus 2 is 22, O2, N2. So then we do 12 times 12 is 144, plus 22, plus 32 plus 28 gives us 226. So that's our molecular mass of the repeat unit. So then we do 21500 over 226, and that gives us 21500 over 226 gives us 95.13 something, and then whole number, round it down, 95. This question is about alcohols. Construct an equation for the complete combustion of an unsaturated alcohol with 5 carbon atoms. So unsaturated means it's going to have a C to C double bond in it. So let's just do pent 1, 2, 3, 4, 5 pent 2 in 1O, just to make our lives nice and simple. So that would be C5H9OH plus O2 because it's complete combustion. Well, it's always O2, and then CO2 because it's complete combustion, and H2. Oh, so first we need to balance our carbons. 5 this side, 1 this side. So we're going to stick a 5 in front of the CO2. And then that's our carbons balanced. Our hydrogens, there's 9, 10 this side. 9, 10. And there's only 2 this side, so we're going to put a 5 in front of the water as well. And then all we have to do is balance our oxygens. So C5H9OH. So balancing our oxygens, we've got 3 this side and 10, 15 this side. So what we want to do is we take out this one, that gives us 14 left. So we put a 7 there, and that gives us a balanced equation. Many alcohols, including ethanol, are soluble in water. Explain with the aid of a diagram why ethanol is soluble in water. Well, we're talking about solubility in water. And what's that? Well, we know solubility is when water gets in between molecules. So if we draw our lone pairs and we put our charge on our water, and we know that this hydrogen bonds to a lone pair on an oxygen, and then there's a H there, there's ethanol, so CH, H, C, H, 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 and then we must label this. And we want to put our dipole there, a dipole there, and we want to say this is a hydrogen bond. So the OH group in alcohols makes them suitable for hydrogen bonding. The solubility of hexane 1-ol and hexane 1,6-diol in water is shown below in table 19.1. Explain the difference in solubility of hexane 1-ol and hexane 1,6-diol. Hexane 1-ol looks like this. Hexane 1,6-diol looks like this. 1, 2, 3, 4, 5, 6. Yeah, that's perfect. So what's the difference? Well, 2 OH groups here. So hexane diol 1,6-diol contains 2 OH groups. And what have we just said? Well, more OH groups means more hydrogen bonds. So can form more hydrogen bonds with water. Notice how they say solubility in water in the question, so make sure you put it in your answer. Alcohols are important in organic synthesis and can be formed by the reduction of carbonyl compounds. Complete the flowchart by filling in each box. So here we've got an alcohol, and that's coming from a carbonyl group, and it can only be 1, 2, 3, 4, 5, 6, 3-methyl. So what reagents do we need to do that? Well, it's going to be our sodium borohydrate, which is that. And we don't need anything else for that one. What do we get when we react it with sodium bromide and acid? Well, the acid's going to break down the OH group. It's going to break down the bond between the OH and the carbon. And instead, we're going to get 3 there. And that's going to become bromine. And we're going to get NaOH as our other product. You don't need to write that in, I was just explaining it. So then we're going to use acid catalyst and heat, and it's going to give us 2 structural isomers. Well, we know that acid catalyst and heat, what that's going to do is it's going to take away our OH group, it's going to dehydrate it. And dehydrating turns it into an alkene. So if we draw our hexagon, we draw our other hexagon, put our methyl groups in. So if the OH was here, let's just put it in red. If the OH was here and now it's gone, and it's taken another hydrogen with it, OH, then this hydrogen here. If it takes a hydrogen with it, then these two come out, and a double bond forms here or here. And those two are structural isomers of each other, so those are our 2 products. What is the name of compound K? Well, I thought I did. I scribbled it out, so I have to unscribble it out first. So, excuse me, we've got cyclohexanol here, because our alcohol takes priority, so it's cyclohexanol. And then if we're saying that the OH group is at position 1, we want to keep our locant number as low as possible. So if that's group 1, that's group 2, that's group 3. So it's going to be 3-methyl cyclohexanol. Methyl, can't fit it in. So we go all the way back down. What did we say? We said 3-methyl cyclohexanol. Butanol can be oxidized to form 2 different organic products depending on the reaction conditions used. Describe both oxidation reactions of butanol. Describe in each the structure of the organic product, a balanced equation, and the essential reaction condition, and use square bracketed O to represent the oxidizing agent. So butanol looks like this, and we know that this is a primary alcohol because the carbon that the OH group is on is only bonded to one other carbon. So what do we know about primary alcohols? Well, when you oxidize them, they can either form an aldehyde or they can form a carboxylic acid. So let's start with the aldehyde. So part 1, the structure of the organic product. Well, we've just done this. 3, 4, and then double bonded to the O. 2, a balanced equation. So we're going to take our C4H9OH, react it with our oxidizing agent, and that's going to give us our aldehyde, which is C4H8O, plus H2O, and is that balanced? Well, we've got 4 carbons, 10 hydrogens, and 2 oxygens on both sides, so yeah, that's balanced. And then part 3, the essential reaction conditions, where we need to distill it. And we need K2CR2O7. Now that's not in the mark scheme, but you know, it can't hurt to write it in. Takes 2 seconds, and it could be an extra mark. It's not in this question but if you had a question similar to this, it very much could be. So then we've got carboxylic acid. So again, we've drawn it already. 1, 2, 3, 4. Double bond to the oxygen and an OH group. 2. Write the equation C4H9OH plus oxidizing agent gives us C4H8OO, or just O2, O2 will do it, plus H2O. Now this isn't balanced. Let's just check. Our carbons, we've got 4 on either side. Our hydrogens, we've got 10 on either side. Our oxygens, we've got 2 on this side and 3 on this side. So how are we going to balance it? Well, we'll just put a 2 in front of the oxidizing agent. And then finally 3. This time we're going to reflux. And again, just can't hurt. A chemist analyses a naturally occurring aromatic compound. The percentage composition and mass spectrum of the compound are shown below. Percentage composition by mass: C70.58%, hydrogen 5.92%, and oxygen 23.5%. And this is our mass spectrum. Determine the molecular formula of the compound. So we're going to use our percentage composition to do our empirical formula first. So CHO, so we're finding the ratio of these molecules. So we do MMRN. We're going to imagine we've got 100 grams, in which case carbon's going to take up 70.58, hydrogen's going to take up 5.92, and oxygen is going to take up 23.5. Divided by the MR, 12, 1, and 16. 5.92 divided by 1 is 5.92. 70.58 divided by 12 gives us 5.88, so 5.9, and then 23.5 divided by 16 gives us 1.5 or 1.47. So then we divide by the smallest number, so that's 1. 5.92 divided by 1.47 gives us 4, and then it's going to be the same for this one. So it's 4 to 4 to 1. So we're looking at C4H4O, and then we need to find the MR of this. So 48 plus 4 plus 16. So 48 plus 4 plus 16 gives you 68. So that is our molecular mass of the empirical formula. So now we want to find what the molecular mass of our actual molecule is. So if we look at our graph, take our second largest peak, which is about here. Hang on. It's this one here, second last peak, not our second biggest. It's about here. So then this one here, this tiny little one here, is going to be our M+. So if I just zoom in, just so I can see it better. So it's saying that's our M+, and then this one here is just from carbon 13, so we can ignore this one here. So this one here is at 125, 120, 130, 132, 137. Okay, so I might be wrong here. Yeah, I am. So we're going to use, rather than that little peak, sorry, we're going to use this larger one. So that's at 136, and then 136 divided by 68 gives us 2. So we're going to double everything in our empirical formula. So it's going to be C8H8O2. Qualitative tests are carried out on the aromatic compound. The results are shown below. Determine the functional groups in the compound and explain your reasoning. Well, first of all, we've got some sort of acidic compound. So that's good to know. But it doesn't react with sodium carbonate, so it can't be a carboxylic acid. So at the moment it's looking like it's going to be phenol, because phenol is acidic, but it doesn't react with sodium carbonate. So 2,4-DNPH, orange precipitate, well, we know that that means it contains a carbonyl group. And then Tollens reagent, no observable change, so we know that this means that it's a ketone. So it contains a phenol group and a ketone. Phenol is present as the aromatic compound is acidic but doesn't react with sodium carbonate, Na2CO3, and a ketone is present as 2,4-DNPH. Change that so it's correct. 2,4-DNP forms an orange precipitate. But Tollens doesn't produce a silver mirror. The carbon-13 NMR spectrum of the compound is shown below. Using the spectrum and the results from A and B, determine the structure of the compound. So it says use the answers for A and B, so we know that the answer for A was C8H8O2, and we know that the answer for B was it contains a ketone and a phenol. So now let's look at our NMR. We're going to call this environment A, B, C, D, E, and F. So let's assign some values to it. This is going to be 27. This is going to be 115. We'll call these two 130. E is going to be 155 exactly, and F is going to be 197. So 27, according to my data sheet, is going to be C to C. 115 is going to be our benzene ring, as is 130, as is 155. So that means we've got 4 benzene environments. That'll be important in a second. And 197 can either be an aldehyde or a ketone. We know it's a ketone, so we'll just put that in there. Okay, so now what do we need to do? Well, we need to draw our molecule. So starting always with our benzene ring. And we know that it's a phenol group, so the OH is going to be here. Why? Well, because in order to be phenol, the oxygen here has to be directly bonded to this benzene ring. So then how do we create 4 environments? Well, let's just call our other group X for the moment. If we put X in position 2, what are we going to do? Well, we're going to get this environment 1, this environment 2, 3, 4, 5, 6. And the reason 3 and 4 are different is because 4 is close to this OH group, but 3 is close to this X group. So they're not going to be the same, they're going to have slightly different environments. And likewise, if you were to take it off and put it on position 3, well, this would be 1, this would be 2, this centre one would be 3, 4, 5, 6, and again 4 is closer to the OH and 5 is closer to the X, hence they're different. So the only place left for it to go is here on position 4. And let's just check, well that's position 1, that's environment 2, and then 3 and 3 because these are the same distance from the OH group and it's symmetrical, and then this would be position 4 and environment 4 and 4 because again same proximity to the X and symmetrical. So now we know that whatever we've got left is going where the X is here. I'm just going to rub this out. We want it to look nice and tidy so we don't lose marks. So what have we got left at the moment? We've got C6 for our benzene ring, H5 because we know there's going to be a bond here so the hydrogen's not going to be involved, O, and we want C8H8 O2. So what are we missing? We're missing an O, 3 hydrogens and 2 carbons. So our X group here is going to be 2 carbon long. So if this is our first carbon, then we're going to be 1 chain longer. So that's that. It's ketone. So the middle one is going to be double bonded to our oxygen. Can't form any more bonds around that. And then there's going to be 3 hydrogens here. You don't need to write them in. It's just there. So it asks for reasoning in the question. Realistically, the reasoning is all here. It doesn't say anything in the mark scheme that you need to have, such and such. You don't need to say any specific keywords. You just need to have some level of labeling the diagram, peaks identified, peaks labeled, and then you can indicate them with text, it says, but again, you don't have to. A little bit of disappointment here for you folks. Compound L is an organic compound containing carbon, hydrogen and oxygen only. The proton NMR spectrum of L is shown below, and the numbers by the peaks are the relative peak areas. Compound L is refluxed with aqueous hydrochloric acid, forming 2 organic compounds M and N, and the infrared spectra is shown below. Well, it's gone. OCR have pulled it off all the examples, all the 2017 papers. Obviously it says here third-party copyright restrictions. I can't find it anywhere. Even it's not there on the OCR website, it's not on any of the past paper sites that I use, or any of the ones that I don't use. So I'm very sorry, but I'm going to cut this question. And it's 6 marks as well. But I'm really very sorry, but we're going to have to cut this one question short. So that's going to be it for this week. Please feel free to join me next week for Unified. As always, I hope this helped you as much as it helped me. Please remember to like and subscribe, and I'm very sorry for cutting it short, but if you feel unable to do those questions, definitely go look up other people's tutorials on them. And I'm sorry again, but I will hopefully see you next week for Unified. See you then. Thanks for stopping by.